The public key cryptography revolution had two parts. The first was public key encryption, which aims at providing privacy of documents. And the second was a new capability of digital signatures. We're all familiar with handwritten signatures, which we create routinely to sign all kinds of documents, checks, and so on. It's a scrawl with security relying on it being difficult for others to mimic one's handwriting and recreate it. Now, with documents that we want to sign moving online, it becomes natural and useful to have a digital signing capability. So how could we get there? The first natural way to do this is to take a handwritten signature and simply digitize it, meaning turn it into bits, which you might store in some image file, and then attach it to documents as a signature. And there are many capabilities and tools out there to create these types of digitized versions of handwritten signatures. We can look, for example, at DocuSketch. You can go there and you can draw a signature. So using my mouse, I can start typing over here and save it. And now it will put that file somewhere. So I can save it, let's say, in a downloads folder and call it my sig. And once I've done that, if I look at the file, then that's the signature. And how do I use that? Well, I simply attach it to documents. But this has a major security problem, which is that the signatures can simply be taken from one document and put onto another. It's just a bunch of bits. They can be detached, copied, moved around. So we recognize here that to be secure in the digital world, a signature must not only depend on the signer and be something only a signer can create, but also depend on the message to be signed. Otherwise, it can be copied from one message to another. Eventually, cryptographers came up with the digital signature primitive, and its syntax looks as follows. A digital signature scheme consists of three algorithms, one for key generation, one for signing, and one for verifying. Key generation will produce a verification key and a matching signing key, which are mathematically related. The signer keeps the signing key, and now given a message M, it can run the signing algorithm on that and get a signature. The algorithm might be randomized, but needn't be. A verifier, to verify this, needs the verification key, but does not need the signing key. Given the message and the signature, it can run the verification algorithm and test whether the signature is actually valid for this message and key or not. As usual, before we consider security, there's a correctness requirement, which says that when signatures are created legitimately through the signing algorithm, the verifying algorithm will accept them. And we can write this as follows. We take a particular key pair, VKSK, generated by key generation. We sign under SK a message M using our prescribed algorithm and verify for the same message, that signature. And we expect to get back 1, that this is accepted. Since signing is randomized, there's some probability this happens, but we just require that to be 1 so that it always happens. The message is drawn from some underlying message space because sometimes we need to limit the set of messages a scheme can sign, and in some cases that space may even depend on the verification key. How we expect all this to be set up and how it will work, just like for public key encryption, key generation is a local operation. Alice on her machine can run SSH keygen or OpenSSL many other softwares which will execute the key generation algorithm corresponding to one of the many popular systems out there, RSA or discrete log systems, and obtain keys, and then Alice will store securely and locally the signing key. Next, Alice will convey the verification key to any entity that may want in the future to verify signatures that Alice produces. Once all this is done, Alice can take a message M and use the signing algorithm to produce a signature on it. And if some entity who holds that verification key obtains the message and signature, it can verify that they really do come from Alice. Now, in this public key setting, we have relaxed requirements on keys because the verification key has no associated privacy requirement. It's fine for everybody to know what it is. But that doesn't mean there's no requirements. We do require authenticity, meaning if a prospective verifier gets a verification key that is supposed to be Alice's, there should be some assurance that really is hers and doesn't belong to someone else. There's many ways this can be done. Maybe one could put verification keys in some kind of trusted but public place, or sometimes people put it on their personal Facebook pages or other personal social media accounts. The more common method is to use certificates in the public key infrastructure, as we'll see later. But for our study of digital signatures as a primitive, we assume this has been done and we study the digital signature scheme itself. Now, message authentication codes, which we studied in the symmetric setting, aim also to provide integrity and authenticity of data. So in what way do they differ from signature schemes? The difference is that they're symmetric. In a MAC, the signing and verifying keys are the same key. A consequence of that is that anybody who can verify is also able to produce MACs, and thus verifiers can actually forge MACs if you view them as adversaries. And that's something that signatures get around. With these, anyone holding the verification key can check Alice's signature under the corresponding secret key, but they cannot themselves generate Alice's signature. And you can see this playing out as valuable in a security application by considering the use of MACs or signatures to sign checks. If you were doing that with MACs, the key would have to be shared between the signer Alice and whoever is verifying, let's say her bank. But that creates a danger. Perhaps the bank servers are breached, in which case that key is compromised, and now the adversary has it and can start forging Alice's checks. If instead we use signatures, what the bank holds is Alice's verification key. If the servers are breached and that's recovered, the adversary is not able to forge Alice's checks. So we move on now to formalizing security, and it's very similar to message authentication. The only difference really is that there is a verification key and we need to ensure the adversary has it because it's public. The intent that this definition aims to capture is to consider the adversary having as goal to get a verifier to accept something as Alice's signature of some message. As long as that's not true, meaning at no time in the past has Alice actually signed that message, then our adversary should fail. Furthermore, this should be true even if the adversary can collect Alice's signatures on other messages, and even if those messages are chosen by the adversary. As in our study of message authentication schemes, we don't require here that security hold against replay, not because that isn't important in an application, but because it's an abstraction boundary useful to draw to separate this authentication the way we see it and add replay on top with counters or timestamps or whatever. So here's the game. It's again called UF-CMA for unforgeability under chosen message attack, but you can disambiguate with MACs by the fact that the subscript is a digital signature scheme fixed here with its 3 algorithms as the object whose security we're measuring. Initialize runs key generation that gives it a verification key and matching signing key. It returns the verification key, so the adversary has that up front. And it initializes a set to empty for bookkeeping. Now, to understand this, it's useful to first begin by looking at finalize. Finalize represents the verifier and represents what the adversary needs to do to win, which means it needs to come up with a message and some candidate signature which is actually correct. What does it mean to be correct? When the adversary supplies these, the game will run the verification algorithm of the scheme with the verification key here on the message and signature supplied by the adversary to get a decision bit. And if that decision is accept, meaning the bit is 1, it says, okay, the adversary has won the game. Now, additionally, the adversary has a capability of attacking the signer. That takes place through this oracle or procedure. The adversary supplies a message, and the signer obligingly generates a signature of it, holding the secret key SK under which it's done. In the game, it's the one over here. That process generates a signature which is provided back to the adversary. Now, if we left it at that, there is a trivial way for the adversary to win. Go to sign with some message, get back a signature, submit here that same message and signature pair. Obviously, by the correctness condition, verify will be true and it will win. But this isn't really capturing what we want, because here the adversary hasn't done any harm. The message was authentic. The signer actually agreed to sign it. The way the game rules this out is by collecting in this set S all the messages that are legitimately signed and then allowing the adversary to win only if the message it provides is not one of those. As usual, the winning is an event in this game which has a certain probability, and that probability is the advantage of the adversary. The superscript is the name of the metric, subscript the scheme whose security we're measuring, and the argument is the adversary. So now we know what we're looking for with regard to security. This is just a summary to have in writing the things I said on the prior slide, and we can quickly see how those are reflected here. Remember that the return verification key statement in initialize means the adversary gets the verification key as input up front. It doesn't change throughout the game, although there are many change calls to the sign oracle. Of course, the adversary is not given the signing key. The chosen message attack arises through calls to the signing oracle, allowing the adversary to collect signatures. And winning requires 2 things. For the forgery that the adversary outputs the message signature pair, it's correct, it passes verification, and it's new, it wasn't something signed before. In words, what we said before, it's not possible for the adversary to get a verifier to accept as authentic a message unless it really was authentic, meaning signed by the real sender. Let's turn to building signature schemes. One of the nice features of RSA and a motivation for it is that it lends itself quite naturally and easily to digital signatures to arrive at what we call the plain RSA signature scheme. As with all things RSA, there is an associated generator, and that generator will give us a modulus, the 2 primes whose product is the modulus, and matching encryption and decryption exponents. In our digital signature scheme, the key generation algorithm runs the generator, returns modulus and encryption exponent as the verification key, and the modulus and decryption exponent as the secret signing key. And this is common to most RSA-based schemes. Now, if we come to sign a message, we're going to ask that this message be a point in Zn star. This means for us the message space is going to be Zn star. So for the message Y given here, the signer will decrypt it under the RSA function, meaning raise it to the dth power mod n to get X and return that X as the signature. Now we come to verify, which has the message and a candidate value and wants to know whether that is the correct signature of Y or not. It can't compute the signature by raising Y to the D because it doesn't know what D is, but it has the verification key n, e, which contains the encryption exponent. And we know that these encryption and decryption algorithms reverse each other. So it takes the signature and encrypts it under RSA by raising to the eth power mod n and checks if it gets back the message, returning 1 if so and 0 otherwise. So it's easy to see that correctness holds, meaning that the verification algorithm will accept signatures generated by the signing algorithm. So let X be such a signature created under message Y. And let's look at the verification equation and see what X to the power E is. So it's since X is Y to the D, we get this. And that simplifies to this, because remember that in any group, exponents can always be taken modulo the order of the group. And the order of the group here is phi of n. And now the main defining property of RSA tells us that this is just 1. So we get Y to the 1, which is Y. So this check works out and verification will accept. All right, so what about security? Well, to study that, let's recall that once we fix a modulus n and encryption exponent E, we can define the function f from Zn star to Zn star by f of x equal x to the E mod n, and that's RSA encryption. The reverse of that can be captured as the function from Zn star to Zn star that given Y raises it to the dth power mod n. So now we see that creating or forging a signature of some message Y amounts to computing f inverse of Y. And the adversary has the verification key modulus and encryption exponent, but not the D, which is in the signing key. So how can it raise Y to the dth power? In particular, we assume or are willing to assume that the RSA generator satisfies one-wayness, which means exactly that it's hard to go backwards from outputs to inputs of the RSA function. So we expect perhaps that it should be hard for the adversary to compute f inverse of Y here. So is that right? Well, this was actually historically the kind of idea and intuition that led to the proposal of plain RSA signatures and the understanding that they worked. But with our modern perspective, it's not hard to see that this isn't correct. And one of the ways that has become easy is that we have precise definitions of security. And once we consider UF-CMA, we see that it's easy to violate. Intuitively, the difficulty is that in this intuition, when we talk about exploiting the one-wayness of RSA, we recall that that only works or is defined when the range points on which the adversary is required to invert are random points in Zn star. But in UF-CMA, the adversary gets to pick the message. The messages aren't random. So in particular, it picks the message 1. Now we said, well, raising things to the dth power is hard, but not when the thing is a 1. Raising 1 to the dth power will just give you back 1. And so the signature of 1 is 1. The adversary returns that pair and has an advantage of 1. Right? So one-wayness does not mean that it's hard to invert the function on all points in the range. Here's another attack that illustrates how the homomorphic properties of RSA lead to violation of security here. The adversary given the public key starts by picking 2 points in Zn star. They're assumed to not be 1. And it then goes to its signing oracle and it picks and asks it to return the signatures of those 2 points. So now that it has those, it creates as a message the product of the 2 messages here, and correspondingly as a signature, the product of the signatures here. And we claim this works, meaning the adversary has advantage 1. Why is that? what is the signature of the message y1 times y2? Is that raised to the dth power mod n. But by simple algebra, that's the same as individually raising y1 and y2 to the dth powers and multiplying them. But this, from a cryptographic perspective, has a completely different interpretation as this. This is the product of the signatures. So now if we take the individual signatures, we have this. And that tells us that the product of the signatures is the signature of the product, and so this signature is correct. Now the reason we excluded a 1 here is just to ensure that the y1, y2 message here is new. It's not equal to either y1 or y2. Okay, so that didn't do so well. And it's not merely from the security side, but also from a practical usage perspective. Plain RSA has the limitation that the messages are points in Zn star. And what we really want to be able to sign is strings, which could be of arbitrary length, files, videos, whatever, and we don't want to be restricted to 1024-bit integers. So we move to fixing this by throwing in a hash function, what's called the RSA Full Domain Hash Signature Scheme. Again, is relative to a fixed RSA generator and assumes a hash function whose range is Zn star, where n is the modulus in the verification key. So the range of the hash function depends on the verification key. In the algorithms of the scheme, key generation is just like in plain RSA. Run the generator, return modulus and encryption exponent as the verification key, modulus and decryption exponent as the signing key. When we have to sign a message M, we have access to the hash function and we have the signing key. And we're going to do effectively the same thing as in plain RSA of raising y to the dth power, except that y is no longer the message, it's the hash of the message. So having hashed the message, we decrypt the result and return that as the signature. How do you verify? Given access to the same hash function and the public key, modulus, and encryption exponent, we have a message and candidate signature. Since the hash function is accessible and public, we can recompute the y and then proceed as in plain RSA. Encrypt the signature and see if you get back the hashed message. Here, the message space is now all strings. It's the domain of the hash function. But the signature is still a group element. And correctness is the same as before. If you generate a signature according to the above algorithm on a message M, let's just denote by y the hash of M. And then we see that exactly the same algebra as before holds. And now this shows that this algorithm will return 1. So we understand, at least looking forward, that we'd like the generator to provide one-wayness of RSA. But what are the requirements on the hash function? When we studied hash functions, we talked about collision resistance, but we weren't able to give what was perhaps the most important motivation for it, and that's arising now. It's in these digital signatures. And our claim is that collision resistance of the hash function is a necessary property for security of the full domain hash signature scheme and for most other signature schemes which also employ hash functions in this way. The way we see that is, suppose collision resistance was violated. Suppose I'm handed an adversary C that can trundle along and in some practical amount of time return a collision for the hash function H. Remember, that means a pair of points which are distinct but their hash values are the same. Then we can break the RSA full domain hash signature scheme. And the intuition is very simple. It's that we notice that in that scheme, the signature depends only on the hash of the message and not otherwise on the message. So if two messages have the same hash, they have the same signature. And that can be seen in this equation. Suppose I generate the signature of M1 and call it X1, I know it's the hash of M1 to the D mod n. But if hash of M1 and hash of M2 are the same, these are of course also the same, and this is the signature of M2. So the two messages have the same signature. How can I exploit that? Well, not directly, but in UF-CMA, remember we have access to a signing oracle. So what our adversary, given the public key, can do is run the collision finder to find that colliding pair of messages, go to its signing oracle and say, please sign the first message for me. And then by this, if it returns the other message and this signature, it will work. This message is new because it's different from M1. So our conclusion is that the UF-CMA security of this scheme needs the hash function to be collision resistant. Now, one thing to be beware of is that that is a necessary condition but not sufficient. So you could have collision resistant functions for which the scheme is still insecure. We'll have to think more about that in a bit. So now we come at this from the other end. Rather than thinking about necessary conditions for security, we want to think about sufficient conditions and prove security. And that takes us back to the random oracle model. So remember, in this model, when we have a game and we are considering schemes that have access to some hash function, we model that hash function as random, and we do that by adding to the game a procedure that implements this random function. And this procedure can be called by scheme algorithms. Those are run by game procedures themselves if they like, and most importantly by the adversary. What does this procedure look like? On inputs W, it maintains a table HT, and it returns random points in some range set R. And however, it makes sure that if it had already been called on a point W and is called again, it stays consistent, returning the same point as before. What is this range set R? It might depend on the scheme, and in the case of RSA FDH, it's the range of our desired hash function, which is Zn star, where NE is the verification key. Okay. Now for RSA FDH, we need only one random oracle. There may be times when more are required, in which case the procedure will supply perhaps an index for H, which allows you to invoke many random oracles. So now we're going to analyze the scheme in this model, and our claim is that it works. So how do we state that here? Let this be an RSA generator. We're going to need to assume something about that, which will be how we encapsulate an assumption on RSA, and that assumption is going to be one-wayness. Let DS be the full domain hash signature scheme. This is in the random oracle model, so we don't explicitly talk about the hash function. It's part of the model now. I'm given an adversary A attacking the UF-CMA security of the scheme in the UF-CMA game, and it will have some resource users, some number of queries to its sign oracle. And now, since the hash function is itself an oracle, the number of computations of it is measured as queries to that oracle, and there'll be some number of them. And in addition, of course, this adversary has a certain running time. Our reduction will construct from A an adversary attacking the one-wayness of RSA. That adversary is called an inverter and is denoted I. And then the following is true. An upper bound on the advantage of A in violating UF-CMA is the advantage of the inverter in violating one-wayness. That is relative to the generator. But there's a factor here. And this factor says, well, possibly this could get somewhat bigger than this, but not too much bigger. It's limited by this factor. This still works out for security because we can make this extremely small, whereas this is a practical amount, and so the product can still be kept small. The running time of the inverter is close to that of A, but there's some overhead in the reduction. So succinctly, this says that the RSA Full Domain Hash scheme does satisfy UF-CMA security in the random oracle model, the assumption being one-wayness of the generator. All right, so we're now going to see how to approach a proof of this, and this is interesting as illustrating some new techniques and methods in the use of random oracles for proofs. And these methods are quite ubiquitous and arise in many other cases. In particular, we're going to illustrate something called programming. We're going to do this proof incrementally to get some intuition. So the way that works is we're going to start by making various assumptions on the adversary, restricting ourselves to certain special cases, and then slowly drop those assumptions. Now remember, our adversary is allowed to make some number QS of queries to the sign oracle. In the first cut, I'm going to simply assume that it fails to use this capability. This adversary makes 0 queries to that oracle. That should make my task easier. The adversary also is allowed to make some number QH of queries to its random oracle H. But I'll assume it makes only one such query, and I'll just denote that query by M. Finally, the adversary is supposed to return a forgery consisting of a message and a candidate's signature, and it wins if they match up. So I'm going to assume that the message in the forgery was in fact the one that was in the hash query. Now this is not much of an assumption. The adversary has pretty much no chance of winning unless it does query its forgery message to H. But in any case, to make it clear, I will explicitly assume that. Now my job is to build an inverter. The inverter takes input as per the definition of one-wayness that we gave for RSA, the modulus, the encryption exponent, and a target point y. This point y in the game defining one-wayness is drawn randomly from Zn star. So for us here, we think of it as a random point in Zn star. And I wants to know what is y to the power d mod n. How is it going to compute that? Well, it remembers that x here is the hash of m to the d mod n. In order to compute the correct x, the forger is raising the hash of m to the dth power. Our adversary is thus going to arrange that what the forger thinks is the hash of m is this y over here. How does it do that? When it runs the forger, it simulates the hash oracle. It has to give the forger the public key first, of course, so that otherwise the forger won't run, but that it has from over here. When the forger makes its unique query to the hash oracle, the adversary simply returns y as the response. It can make up whatever it wants here, and it uses this point here. What is the result? If the forgery is correct, then x is the hash of m to d, which is this. But we've set the hash of m to y, and so we get x as y to the d mod n. But that's exactly the condition for the inverter to win. And so we've recovered the UF-CMA advantage of A as the probability that the inverter violates one-wayness. All right, so that was simple enough, but remember it relied on a bunch of assumptions about the inverter that limited it. And it's not the formula in the theorem statement, it's actually much better. And that tells us that as we drop those restrictions, there'll be some price to pay. Proceeding incrementally again, I'm going to continue to assume no sign queries. But now I will allow many H queries from our adversary. So it has Q sub H of them, and we'll denote them by this list. Of course, again, it outputs a forgery, a message and its candidate signature. And again, I'll assume that the message was queried to the H oracle. I don't know in advance which element in the list it was, but I know it's somewhere in that list. All right, we now have to design our inverter I again, which manages to find y to the d mod n given ne and a random y over here. So why don't we proceed just as before? We know that if the forger wins, x is hash of m to the d. So if the reply here to the hash of m is y, then we know that the x is going to be y to the d, which is the quantity the inverter wants. So that's what it proceeds to do. It runs A with the simulated hash oracle on input a public key, gets the message and signature, and returns the signature. How does our analysis proceed? Well, we know that the message that's output in the forgery is somewhere in this list. I don't know where, But for the analysis, let's denote the index by I such that m equals m sub I. Well, if A wins, we know that x is the hash of m sub I to the d mod n. But regardless of what I was, this hash has the value y. So we get that this is equal to y to the d mod n. But since that's the quantity that the inverter wanted, it succeeded in inverting y, and so it should win. And correct? Well, it looks plausible, but there's a little bit of a problem, and it's not correct. And what exactly is wrong is that when you run this algorithm A as a subroutine, you need to give it the environment it expects through your simulation of its oracles. If you don't do that, you have no guarantee as to what it's going to do. How does that come up here? Look at how I is replying to H queries. All of them are replied to the same way. If you make two different H queries, you get the same thing back. Well, that will cause A to get extremely suspicious, because in the real execution in its UF-CMA game, H is a random oracle, and it's getting back random points to each query, and they're very unlikely to be the same. Put more formally, the answers to H queries need to be independently and uniformly distributed over Zn star. And that is not happening here. This is uniformly distributed due to that being true for y, but the queries are not replied to with independent values. And you could even construct a counterexample. Consider an A making two distinct queries, but whenever it gets back the same answer, it aborts, and otherwise it goes on to create a valid forgery. So this adversary will have a high advantage in the UF-CMA game, but our inverter will have a very low advantage because it will hit this case over here. So what that tells us is we need to reply to these H queries correctly with random points that are independent across different queries. And here's how we're going to do that. When we consider this constraint of replying in that way, we realize that we have conflicting goals for our inverter. I do want that y is the reply to the hash query on this message, because that's why x, which I return, is going to be the correct inverse of y. But I can't reply by y to all messages. What do? Well, I could say, okay, everything except m, I don't really care about, and I'm going to reply with a random value in Zn star. That is good, but the problem is I don't know where m is in this list a priori. How do I resolve that? I make a guess as to where it is. So what our inverter does is it picks a random index in the range from 1 through the number of hash queries of A, and initializes a counter to 0 and starts running A, and it will, as usual, simulate the hash oracle. What it does in that simulation is it says, I'm going to index the queries made, all q sub h of them, and so every time one comes along, a new index is allocated. Once I get to the gth query, where g is what's here, I'm going to think that that's what this is, and accordingly, I will set my reply to be the challenge over here. But otherwise, if I'm not at that crucial index, I'll just return a random point in Zm star. Okay, well, what have we gained? Certainly one thing we've gained is we notice that the replies to the queries here are all random independent Zn star strings. So now A will not see anything weird about the responses it's getting, and it'll trundle along and it'll win with whatever probability it's supposed to win in the UF-CMA game, which is this over here. Okay. So in that sense, this will be correct in the sense that x will really be hash of m to the d with this probability. However, that's not always going to help the inverter. It will only help the inverter if m was also the gth query, because that's when it planted the y whose inverse it wants. So suppose that happens. Suppose that the adversary A wins, and also the inverter got lucky and managed to correctly guess the index corresponding to the forgery message m. Well, in that case, we see that since X, by the correctness of the forgery, is the hash of Mi to the D, and since I equals G, that will also be the hash of Mg to the D. And since that value was replied to by Y, we get Y to the D. And so the inverter indeed wins. So now the final step is that how likely is it that the guess is correct? Well, there are Q sub H things to guess from, and so with 1 over Q sub H probability, the inverter will guess correctly. And so its advantage is 1 over Q sub H of that of A. It's diminished relative to the advantage of A, but by a controllable amount. And if you look at the theorem statement, it's effectively transposed this to a multiplier over here. Now, there's an important element in this argument here, which is that you can think of A as knowing that this strategy is happening. It can be thought of as trying to make sure that the forgery messaged outputs is not going to be in the gth position. But it's going to fail at doing that. And why is that? Because it has no clue what this G is. It's chosen at random over here, and the replies that A gets back are uncorrelated to what G is. They're just random Zn star elements. And so an important part of this proof is the argument that A has no information about this guess. And that's how you get to multiply these two probabilities, because they're independent of each other. Now, this whole proof needs to be gone through more slowly. If you were writing this in an assignment, you would need more details and justifications and some care in making the arguments. But let's go on. We have still one more case to deal with. We have not yet allowed this adversary A to use its signing oracle. So let's assume it does that. It now has queries also to the signing oracle. But this creates something which is almost paradoxical. Indeed, in early discussions of proofs for RSA signatures, there was a paper which called this a paradoxical problem, which couldn't really be resolved. And the paradox is as follows. We are trying to design an inverter I who does not know the decryption exponent. It needs to run our UF-CMA adversary A. This UF-CMA adversary A will request a signature now and say, here's a message M, please provide me hash of M to the D. If our inverter wants to continue to run A, it has to supply this, and it has to supply it correctly. There's no way to give back a wrong value because A could check it. But this seems impossible. How am I going to raise H of M to the D when I don't know D? Why is it paradoxical? Because the goal of the inverter is to raise its input Y to the D. If it can raise things to the D, it doesn't need A at all. It could just raise Y to the D and be done. So how is this possibly all going to work out? The answer is that the inverter controls the random oracle. It simulates it. So what it's going to do is play with that. And it's going to look at the fact that this is the hash of M to the D. And so it expects that prior to the sign query, M was queried to H. When that happens, the inverter will say, okay, I believe in the future I will be asked to sign this. So I need to create hash of M in such a way that I can raise the result to the D. And there's a trick to do that. What you do is you don't create a random point in Zn star as the answer, but rather you start with some other random point in Zn star and encrypt that under RSA and provide that as your answer to the hash query. Right? So the answer to the hash query is a point in Zn star, but of a specific form. It's the encryption of another random point, and our inverter knows what the xj is. Why is this helpful? Now, what is hash of mj to the d? Well, it's xj to the ed, but ed is 1, so it's just xj. And so this value here is the signature, right? And this is what's called programming the random oracle. Well, we've been doing that for a while, but this is a use of programming the random oracle and allows us to simulate signing. Now, some things that one needs to note here. Remember that replies to H queries need to be random independent points in Zn star. This looks structured. Why is it of that a random point in Zn star? Because xj is random, but that's not enough. The second point is that raising to the eth power is a permutation on Zn star. So random points map to random points. Okay? If this function a raising to the eth power had not been a permutation, this would not be uniformly distributed. So that's the intuition. So let's now put it together. Towards that, it helps to make a few simplifying assumptions on the adversary. These assumptions, unlike the ones we had before, are without loss of generality. So one of them is that if the adversary queries M to the sign oracle, it has previously queried M to the hash oracle. Another assumption is that when the adversary outputs a forgery, a message and candidate signature, it has prior to that queried M to the hash oracle. Now remember that if it queried M to the sign oracle, it wouldn't win the UF-CMA game. That's disallowed. So we assume it doesn't do that. That's natural, otherwise it wouldn't win. It's also useful to assume that H queries are not repeated. It never helps to repeat because you just get back whatever you got before. So we'll assume it never happens. How do we make all these conditions true? We just make small modifications to A, throwing in extra hash queries or memoizing them as necessary to make this true. It has a small cost. We can now think of A as making this many hash queries. Effectively, Q sub H is replaced by this Q over here. And with that, what we go on to do is give the final construction, meaning we're going to give our inverter in the setting where there are no restrictions on the number of sign queries, hash queries that we've made before. We have to bring in all the ideas we've seen so far to do that. So our inverter gets as input the modulus and encryption exponent and the challenge point y, and it will continue as before to guess a hash query, which is where it wants to plant this point y. And we see that again here. When the index in replying to hash queries hits the guess, we populate the table at the corresponding message with our challenge. And eventually that's what we are returning. Okay, the change is what happens when you're not at this guess, right? What you do is you pick xj at random as per our last slide intuition, and you put as the reply to the hash or query xj to the eth power mod n. What is all the rest of the stuff? We need some bookkeeping. So we're going to store the values of h in this table. And we're also going to reverse index. The map ind takes a message and returns back the index, meaning when it was a hash query. Remember that all messages that are going to be signed were hash queries at some point prior to that. And so every such message has an index j. What happens when we get a sign query? Well, now A has access to the sign oracle and an inverter has to simulate that. And the way it does that is it says, here's a message M. I know it was a prior hash query, and through IND I can recover the index. That enables me to retrieve the point xj here, and that is the correct signature by the arguments we gave on the prior slide. And so that's it. So now suppose we do the analysis before. Mathematically, there is some index I such that the forgery message was the ith one queried to the hash oracle. Remember, we assumed that it was one of the messages queried. So now suppose A wins, meaning hash of M to the D is equal to X, but also our guess is correct, it's equal to this I. And then it's as before. We see that all of the queries of A are correctly answered. That is where a lot of our work went into making that to be true. And all these choices here, the fact that RSA is a permutation, and so forth are involved in justifying that. And otherwise, as before, the winning of A means X is the hash of Mi to the D. The fact that I equals G means that's the hash of Mg to the D. And the fact that the hash of Mg was set to Y over here means that's Y to the D, so the inverter wins. Again, the guess is correct with probably 1 over now Q, since Q is the number of queries to H. And the adversary has no information about what G is, so the chance of this guess being correct and the adversary winning are independent events, and we multiply their probabilities to get the one-wayness advantage of I. When you transpose terms, you get the theorem. All right, so that ends our proof of the theorem, and it's good to go back over that and check that one understands the different subtleties and details. As one goes over it, different points will come up and need to be settled. Now, remember what this theorem did is that it upper bounded the UF-CMA advantage of an adversary by some multiple of the advantage of an inverter trying to violate one-wayness of RSA. So after the result we saw earlier, another one emerged which looked at that factor in the prior result and reduced it. Remember, the prior factor had a term in it corresponding to the number of hash queries. This new result says everything is the same as before, except this factor only depends on the number of signed queries. This is better. Why is that? Because the number of signed queries is typically much smaller than the number of hash queries. In real life, this is the number of messages signed by Alice, and that is either small or can be kept small, whereas this is the number of computations of the hash function that an adversary performs, and the adversaries may have enough resources to do quite a lot of hashing. So we have what we call a tighter reduction. The advantage of this is that the security of the signature scheme is more closely tied to what we understand as of the one-wayness of RSA. And in particular, if you want to achieve a particular level of security, for example, 128 bits, then the size of the RSA modulus you need to do that, which is called the security parameter associated with the generator, is smaller if you use this theorem to justify and compute your choices than if you use the prior one. The benefit of that, of having a smaller security parameter, is actually efficiency, because the operations in the scheme are modular exponentiations which take time cubic in the security parameter. The smaller the security parameter, the faster you are going to sign and verify. So moving forward, we would like to pay attention to this notion of reduction tightness. And we notice that here things improved, but they could be even better. Ideally, this term would exactly match this. There would be no multiplier. Now it turns out that at least as long as we stay with the one-wayness assumption on RSA, for this scheme we don't particularly have a way of doing that. And as we will see in a bit, that has led to another alternative scheme. Before we get there, however, let's discuss the more practical aspect. In RSA FDH, we needed a hash function, and that hash function had range Zn star, where n was part of the verification key. How in practice are we going to build this so that it resembles a random oracle as required in the proof to the best extent heuristically that we can ensure that? The difficulties arise from a different type of range. This is not the set of strings of some length, it's integers mod n. So let's start as follows. First, we'll let G be an extendable output length function. That means that it takes two inputs. One is the input W to be hashed, and the other is an indication of how many output bits we want. And it'll give you an output that's L bits long. There are constructions of this that are out there, standardized and created for the purpose, and one of them is Shake256. So you could simply set G of W and L to be the Shake256 function on the same inputs. If you prefer to use a SHA-2 family function like SHA-256, you might proceed as follows. You start applying SHA-256 to W. That's not quite enough because this only gives you back 256 bits and you may want more. So what you instead do is you apply SHA-256 to perturbations of W, say created by prepending a 1-byte representation of a counter, and you keep incrementing that counter. And that gives you a quite long sequence of bits, a sequence at length at about 2 to the 8 times 256. And now you look at this sequence and your G function will take as many bits as it needs from it, the first L bits. Of course, this requires an upper bound on L so that it doesn't exceed the number of bits in this sequence, but that's almost usually true. And if it isn't, you just make those 1-byte encodings 2 or 3 bytes or whatever. Okay, so this is an XOF. It's not yet what we need. So let's go to the next step. We have an RSA generator which generated the modulus n we're looking at, and it had a security parameter. According to the definition of the generator, the modulus is in the range between 2 to the k minus 1 and 2 to the k. So we know that we want strings of length k minus 1 effectively. So the simplest thing to do is set the hash of m to be our XOF function on m, asking for k minus 1 bits of output. That's okay. We can think of the output as a point in Zn, and it is in the right range almost, but it isn't quite looking random oracle-ish. Why is that? Because all the points you get are below 2 to the k minus 1. And so points in the range from 2 to the k minus 1 up to around n are never returned as outputs. And this could be approximately half the points. So half of the potential range is excluded, and random oracles don't do things like that. So let's try something a little different. We're going to run the extended output function to get not k minus 1 bits, but a lot more bits than we need, twice k bits. Okay, remember we actually do need k minus 1, but with some structure. So when we have those 2k bits, we view the result as an integer and take it mod n. The result is that we do get values in Zn, and these, if G is random, are going to be kind of close to uniformly distributed. So in that sense, things are looking fairly good here. There's one final point that needs consideration. All this is returning outputs in Z mod n, but we want them in Zn star. The difference is just that points which have a GCD different from 1 with n are excluded as outputs of our hash function. So what do we do about that? Well, there's a number of things you could do, but probably the simplest is to just ignore this. For various reasons, it shouldn't really happen often enough to be damaging or make a difference when it happens. And a few lines of argument for that are as follows. So first off, we need to worry about the correctness of the signature scheme. What comes to our help there is there's a mathematical fact that we talked about the RSA function as a permutation on Zn star. It actually is also a permutation on Zn with the same inverse. This is only true if n is a product of two distinct odd primes, but that's true for the numbers returned by our generators. And this is the property that we need for correctness. What about security? Well, if you manage to generate a non-zero point which is in Zn but not Zn star, meaning has a GCD different from 1, a positive GCD with n, you will actually have a prime factor of n. That will be a factoring algorithm. The likelihood of outputs of some hash function factoring in this way is quite small. And so I'm going to assume it's not going to happen and security is maintained. There are other things one can try. Okay, so with that, let's go back to the theoretical side. So remember where we left off is we had motivated getting improved and tighter reductions. We want to tie the security of RSA not just qualitatively but quantitatively to the one-wayness of the inverter so that we can justify use of smaller moduli and thus improve efficiency without sacrificing security. So PSS, which stands for Probabilistic Signature Scheme, is going to be a scheme that does that. Again, there's some underlying RSA generator with security parameter K, and there's another parameter we'll denote by L, and it has to be chosen such that twice L is a fair bit smaller than K. We'll need this time not one but 3 hash functions. The first 2 return L bits, and the last returns K minus twice L in a bit bits. So as examples, you could set K to be 2048, that's a nice RSA modulus size for security, and you could set L to be 256. Let's start by just saying what is the key generation algorithm, because it's the same as with our other RSA-based schemes. You run the generator, you return modulus and encryption exponent as the verification key, and modulus and decryption exponent as the signing key. So here's what signing and verifying look like in PSS. And rather than trying to parse the details of the code, let's try to give some idea and intuition. So in FDH, we hashed the message and raised that hash to the dth power. Now, if you remember what happened in the proof, the loss that led to this factor Q came from the fact that we needed to guess which hash query corresponded to the forgery. And that was important because all the others we had to answer in a special way that allowed us to sign those messages later. What we're now going to do is randomize the hash. We're going to pick a random value over here and append it to the message before we hash. What this does for us is that an adversary cannot predict ahead of time, namely before the signing query, what is the corresponding input to the hash function that will be needed in the signing process. And that is how security is going to improve. Now, eventually, it's very similar in the sense that something is going to be raised to the dth power to get us back our signature. What is that something? Well, we'll include this randomized hash. Now, you might think you could end there, and you could if you also supplied R in some way, because R is needed for verification. But to not increase signature size, R is kind of packaged back into this point. And that's done by rehashing this point and XORing with R. This is again a sort of a Feistel type trick. And so here you put the effectively encrypted R value and this and another hash of W. The reason these are put is that it kind of randomizes Y, and Y to the D is the signature. Okay, how do you verify with access to your 3 functions and the verification key? You have your message and candidate signature. First, recover Y by raising X to the eth power mod n. This is where all the security comes from. This is where RSA is used. Now parse your Y so that it looks like this over here. In order to check that W is the hash of M and R, we need to recover R. We can do that by reversing this equation. So we compute H2 of W, add R star to it, and get back R. But then we check that the hash of W is equal to the last thing over here. And if that fails, we're going to return 0. Also, we want the first bit to be a 0, and otherwise we fail. And as long as all that is true, we finally check that indeed W is the hash of M and R. And if all the checks succeed, we return 1. So we're not going to go through here a full proof or analysis of all this, but we're just going to quote the result and see how it differs for that from FDH. The setup is the same. We fix our generator. It has a certain security parameter. We fix this other parameter L and consider the full domain hash probabilistic signature scheme. we are given our adversary making some number of sign queries and some number of queries now to 3 random oracles, and this is the sum of the number across all of them. We construct our inverter violating one-wayness of the RSA generator, and we see a closed tie. There's no multiplying factor here, so the bound on this is this, and there is an additive term. But this additive term is easy to neglect because it's resources of the adversary divided by 2 to the power r parameter, and a reasonable choice of this parameter will render this negligible. This term will definitely dominate across these two over here. So we conclude not only that RSA PSS is UF-CMA secure in the random oracle model, but with a reduction that we call tight. The lack of this multiplying factor means that the security of the signature scheme and the generator are pretty much the same. And so if you know that you can pick a RSA models of a certain size and ensure by studying factoring that that has a certain difficulty to factor, then breaking the signature scheme will require exactly that effort. You can use the same modulus size. And so you have kind of an optimal efficiency. PSS is quite widely used, and it goes into a number of standards. PKCS number 1 is a standard originally put out by RSA Corporation, and it's the most influential. It percolates into many other standards, and RFC 8017 and PKCS number 1 are kind of the same, and there's also many other such things. So here's a little exercise which asks you to break an RSA-based scheme.